It's my pleasure to introduce Professor David Perreault from MIT. David likes Boston a whole lot, went to Boston University where he received his BS, and he has his master's and PhD from MIT, all in electrical engineering. He's currently the associate head of the Department of Electrical Engineering and Computer Science at MIT. His research interests include design, manufacturing, control techniques for power electronics and components. Dr. Perreault is a fellow of the IEEE, and he received the Richard M. Bass Outstanding Young Power Electronics Engineer Award from the IEEE Power Electronics Society, and the ONR Young Investigator Award, and the SAE Ralph R. Teeter Educational Award. So without further ado, I look forward to an excellent talk from Dr. Perreault. Thank you.
Thank you. It's really a pleasure to speak to you today. I'm going to be talking about design of power electronics operating at very high frequencies, or approximately between 10 and 1,000 times the operating frequency of typical power electronic converters. Before I go into that, maybe it's just appropriate to give you some context on, first of all, what power electronics are and why we really need some innovation in this area. The function of power electronic converters is wherever you need processing and control of electrical energy. So you either want to convert forms of electrical energy or you need to precisely regulate its flow. And traditionally, many loads and sources in the electrical system didn't require power electronics, but as devices have gotten more and more sophisticated, now in modern systems you need very precise regulation. So to give you a sense of that, if I want to create light just by heating up a piece of wire until it glows, that doesn't require very much power electronics, but it's also hideously inefficient. On the other hand, if you want to generate light with a light-emitting diode, then what you need is something that goes between the high voltage AC and the precisely regulated low voltage DC voltage and current at the LED, and that's the power electronic function in the middle there. And you need this for high efficiency LED lighting. You need this for all kinds of computer and communications equipment. Requires very precise regulation. Going in the other direction, if you want to have a solar photovoltaic system where you're going to take DC energy and deliver it to the high voltage AC grid, you need some power electronics function that's going to provide that. And so there's really been a changeover in the electrical sources for renewables and loads that have occurred. So it's been estimated that in about 2005, perhaps 30% of all the energy generated flowed through power electronics somewhere. It's expected to be approximately 80% by the year 2030, and frankly, I think those estimates are low. The other aspect that's important, and why do we need some innovation in this area, is because pretty much the power electronic circuit's often a major factor determining the physical size of the system, the functionality, the performance, and the efficiency. So to give you a sense of that, in this simple example of the LED lighting, you can see that a large portion of the physical envelope of this device is actually consumed by the power electronic component. You can also see that in devices such as hybrid electric vehicles. And not only is it a function of size, but it's also a function of cost. So if you think of the high cost of LEDs, LED lighting, a portion of that is due to the cost of the driver. Likewise, the same is true in the balance of plant and photovoltaic systems, where the actual solar cells are only a portion of the system, and in the electronics is a substantial fraction of the cost driver of the system. Moreover, the functionality of the system is often limited by power electronics, as is the efficiency. So if you think of, you go type in a Google query, that Google query is executed in a data center somewhere, okay? In the data center, in a given data center, there's typically 3 to 4 layers of power electronics between the high voltage 3-phase AC coming in and the low voltage, say, sub 1 volt DC being supplied to the microprocessor that's actually executing that query. And each of those layers of power electronics has dissipation. So you may actually get less than half of the energy coming in from AC that's actually getting to do your Google query for you. And so there's a tremendous waste of energy. And that's true in this example too. In the LED lighting system, somewhere between 10 and 30% of the energy, the AC energy coming in here, never even gets to the LED. Never mind the losses in the LED. It never even gets there because it's typically lost in the power electronics. So we really need a tremendous amount of innovation in energy conversion in order to enable future features, more sophisticated uses of electricity, and to get higher efficiency in these systems. Now, how does a power electronic converter work? What is a system? Well, generally we're trying to process energy without losing any, without dissipating any. So you build power conversion systems out of ideally lossless components. First of all, energy storage components, such as inductors, capacitors, and transformers, and semiconductor devices used as switches. And we want to use things as switches because the product of voltage and current, the dissipation in those devices is ideally zero. If your switch is open, it has voltage but no current. If it's closed, it has current but no voltage, and hence ideally that's a lossless element. So we're going to take together switches with energy storage elements and build energy conversion systems. So the way this would work is you'll configure your switches, you'll draw some energy from the input, you'll transform it in some manner, you'll then use configuration of your switches to transfer it to the output, and you'll operate that cyclically at some rate to process energy, at some switching frequency in order to make that happen. And then additionally, you'll have some input and output filtering that ideally, again, lossless, in order to provide waveform smoothing and give high waveform quality and limit electromagnetic emissions. So you can see an example of this here. This is actually a voltage regulator module for a microprocessor system. Here you can see some input filter capacitors. These intermediate energy storage is the magnetic in the inductors here. And then you can see the power transistors. These are semiconductor devices used as switches. And finally, output filtering provided here. So most power conversion systems will operate in this mode. Now, an important thing to understand about power electronic systems as compared to, say, information electronic systems is they tend to be dominated by and driven by the passive components, the energy storage components and filters. So here you can see a sort of a 25-watt LED driver, and you can see the vast bulk of this thing is made up of magnetic components primarily, and then capacitive components secondarily. And the actual semiconductor content is at least physically quite small. And not only do the passive components dominate the size, they also limit the cost and the reliability and the control bandwidth with which you can control energy. So if you're going to improve power electronics, the passive components really have to be a focus. So the work I'm going to describe today, the real goal is to go greatly up in frequency, or the cyclic frequency of the operation of the system. And what we're really after is three things. The first is miniaturization. I just want to make it smaller. The second is integration. Can we build it in different ways and take advantage of some of the kinds of things where you've seen with integrated circuits as compared to discrete transistor systems. And lastly, getting increased performance, especially bandwidth. And frequency increases give us this because the energy storage elements in the passive energy storage requirements in a converter vary inversely with frequency. And perhaps the way to understand this is as follows. If I thought of energy as a fluid I wanted to transfer, and my passive components are the bucket at which with which I'm going to transfer energy, if I want to go at a certain rate of energy transfer, I can either get a big bucket and scoop that energy slowly, or get a little thimble and scoop very fast and transfer the same rate of energy. And so the benefit of going to a higher frequency is that I can exchange my buckets for thimbles. Perhaps I can build thimbles in ways that it wouldn't be practical to build buckets. And lastly, if I suddenly want to change what I'm doing in the system, I may only be stuck with a tiny thimble full of energy instead of a whole bucket full of energy to do something different. So we can really gain a lot in principle by going to much higher frequencies. However, in the real world, I should temper that a little bit. I talked about the energy storage requirements, and indeed the inductor and capacitor values, for example, do scale inversely with frequency. However, the physical component volume or size that I need actually scales down relatively slowly with frequency due to a bunch of practical constraints, some of which we'll discuss. But in particular, for example, how magnetic core materials behave greatly slows down how much size reduction I can get by going up in frequency. Moreover, if I want to integrate the components or batch fabricate elements in my system, that imposes additional constraints which may limit how quickly I can scale down in frequency. So that's a long way of saying that I may have to go up in frequency very far to get a relatively modest reduction in my overall system size. Now, it's no surprise to anybody who works on power electronics that higher frequencies in principle give you smaller size. It's well established. So the question is, why doesn't everybody do this? And there are a number of practical constraints in terms of going up in frequency. And I'll talk about a couple of these as we go through the talk. One of those is strictly loss. Okay, there are some frequency-dependent loss mechanisms in power electronics that then suggest if I turn up the frequency too much, I'm going to have too much loss and my efficiency goes down and I want to stop, or I have thermal problems. I first of all have loss in my semiconductor devices. I said an ideal switch is lossless, but we don't have ideal switches. We have semiconductor switches. So to give you an example, every time I turn a switch on or off, I am going between current and no voltage and voltage and no current in the switch, but right when I transition between the two, I tend to get some overlap, and that causes bursts of power dissipation, a loss mechanism proportional to frequency. Also, intrinsically, if I have a semiconductor device and I ever turn it on under voltage, well, then I collapse the voltage across the intrinsic device capacitance, and that inherently is going to generate some loss. Likewise, if I'm turning a transistor on and off, I usually do that by, for example, charging and discharging some gate electrode, and that mechanism is itself lossless and is proportional to frequency. Now, how important these relative loss mechanisms are depends upon what kind of system you're building. For very low voltage systems, perhaps the gating loss is dominant. For very high voltage systems, the switching loss is dominant. In the middle somewhere, both of these become important. In addition to the semiconductor device losses, we also have passive component losses, including dielectric loss and conduction loss. But perhaps the most important in terms of limiting the practical operating frequency of power converters is the magnetic core losses, which can scale very quickly up with frequency and hence put a limit on how far one will turn up frequency with a typical design, because eventually your design doesn't get any smaller. In fact, it can start to get larger with frequency, and that's where most designs stop. In addition to just loss limits, I should say that in terms of making power converters miniaturized, reducing their physical size, application constraints also impose a pretty important limitation. So for example, if I want to convert between the AC voltage of the grid, 60 hertz, and DC, it turns out, as we'll discuss later in the talk, there are some fundamental energy storage requirements associated with that which aren't related at all to the switching frequency of the converter. So that's going to impose a minimum size limit on the system. Likewise, if I have requirements of isolation or large conversion ratios or wide operating ranges in terms of voltage or current, these are all going to impact the achievable minimum size of a converter. So they prevent me from just sort of shrinking it down Moore's law style. Lastly, I should point out that different operating regimes put different constraints on the system, and they also require different kinds of devices. So at really low voltages, one might use CMOS, and that imposes some constraints on designs. Intermediate voltages, we might have to use integrated devices for cost reasons, and that's, say, lateral DMOS devices, lateral diffuse MOSFETs. Or high voltages, maybe we can use discrete semiconductors, either silicon or otherwise. And these impose very different constraints on what is practical. So what do we do? What is the objective of this work? Well, it's really to develop technologies that are going to let us go up substantially in frequency and roughly into the HF and VHF range, or 300 to 300 megahertz kind of range. And to do this, we really have a few different thrusts. First is implementation of circuit architectures and topologies and controls that are suitable for running at these greatly increased frequencies. And Second is really to do a better job of leveraging devices, and this includes, in some cases, optimization of integrated power devices and also leveraging new device types that are emerging, such as 3-5 semiconductors. There's also work in the passive components themselves, either making very highly integrated, batch fabricatable passives, and also looking at and developing new magnetic materials that will help us get to these higher frequencies. And last is integration of complete systems and solving sort of all the practical problems, all the corner points that real power electronic designs have to meet to operate out in the real world and satisfy the needs of applications. So to illustrate this, I'd like to show you two different examples today. And the first example I'll start with is sort of moderate voltage and low power, say tens of volts and maybe 5 to 15 watt kind of converter range. And we'll look at an isolated DC to DC converter. So this might be the kind of device you'd use in a power supply application where you have some source of energy and you want to provide energy at some other potential to run isolated circuitry. Okay? So as we said, we have sort of both semiconductor losses and magnetic losses to contend with. And in this range, we're talking sort of tens of volts. Both the gating loss and the switching loss in the device are quite important. And the magnetic loss is also a major constraint and also prevents sort of integrated design. So to address these, we use some sort of these techniques. First of all, in terms of the switching loss, what we'll do is we'll use zero voltage switched topologies. What that means is we're going to arrange circuit topologies such that I never try to turn on a transistor while it's under voltage. This both reduces that overlap loss that I mentioned and ensures that I don't dissipate the internal capacitance when I turn the device on. So I'll make sure the device voltage is already zero when I turn it on. To deal with the gating loss, instead of just charging up the gate and then discharging it and throwing that energy away, what we'll do is try to recycle that gate energy. So we'll use a resonant circuit to ring charge onto the gate and then ring charge back off of the gate and recover that to our power supply. And as long as I'm trying to switch that transistor with a switching rate that's long compared to a gate time constant, we can substantially recover the energy we would otherwise put into the gate. Okay? And this will give us much lower loss than you do with conventional hard gating. So what are the implications of this in terms of the circuit design? First of all, there's a lot of implications. We can't use the conventional kinds of topologies that people use in these applications because they don't meet the constraints. So for example, once you get to sufficiently high frequencies, you can't use topologies where the control ports of your transistors are at flying nodes, right? We're reconfiguring switches. These nodes are flying up and down in voltage, and you can't drive the transistors if their control ports are referenced to a flying node. So we sort of have to reduce ourselves to sort of designs where the transistor reference ports are at slowly moving nodes. Moreover, we have to have topologies that inherently absorb the circuit parasitics. What do I mean by that? In conventional design, what you might do is think of your semiconductor switches as ideal switches, design your circuit, and then the circuit parasitic capacitances or the package inductances are some second order term which I try to manage or ignore, but they're not baked in as part of the process. There's just sort of a secondary loss mechanism. When you get to sufficiently high frequencies, you can no longer do that because these parasitic components become a substantial fraction of your overall circuit parasitics. So in other words, if I have a circuit that has a microhenry inductor in it and I have 5 nanohenries of inductance as a parasitic inductance in the circuit, that's okay. It's negligible. It's a fraction of a percent. If, however, I turn up the switching frequency to 100 megahertz and my overall energy storage inductor is 33 nanohenries, 5 nanohenries of parasitic is an unacceptable amount. So as a consequence, what we have to do is develop topologies that actually utilize the device and circuit parasitics as part of their operation intrinsically. And that's the only way we can get to these extreme high frequencies. Lastly, I should point out, and I should note that this is an example, this is actually a classical RF amplifier topology that illustrates these two constraints. First of all, when you turn this transistor off, the device capacitance rings with the output to generate zero voltage switching. This is a so-called Class E inverter. So I can turn on the device at zero voltage, and so not only do I have a ground reference switch, I have the parasitic capacitance of the device absorbed. So that's a sort of a classical example that some people might be familiar with, where you're trying to take advantage of these ideas to get to high frequencies. I should say that other constraints of this is once you start getting down to these very constrained topologies, you often end up running into a lot of other issues. In this case, for example, because I'm using the load as part of my resonance, I may be very sensitive to variations in this load ruining the performance, say ruining the zero voltage switching of my circuit, so that these topologies tend not to be very flexible, okay? And in a power electronic environment, that's something we're going to have to contend with if we want these devices to operate over a very wide range. So let me just show you an example. This is a inverter topology that we've been using for the number of years now to get to these frequencies, and it illustrates some of these characteristics. So rather than using something like a Class E topology, we pair the transistor with a resonant network that shapes the converter voltage to almost a square wave, very similar to what you'd have in a much lower frequency topology, but without the use of a flying switch. Moreover, because we're using this input side network to shape the switching voltage, it becomes much less sensitive to the load variation. And it also has very small inductor sizes so that it helps us miniaturize. There's no choke inductors in a traditional RF amplifier. So we get very fast transient response out of this device, and we absorb the device capacitance in a very flexible manner. Now, this is a DC in to high frequency AC out, maybe 50 or 100 megahertz output. How do I turn that into a power converter where I said maybe I want to take DC in and generate isolated DC out? Well, what I would do is I would take this and I would implement the same kind of resonant network, but I would bury the resonance in as part of a transformer. Okay, so this resonant network that I showed you on the last page is still in here. It's just buried in the front part of this transformer. The output part of this transformer, what I'll do is I'll create a resonant rectifier. So the device capacitance gets absorbed as part of this, as does the parasitic inductance of the transformer, all to operate in a resonant mode so that everything is soft switched and this can be turned up in frequencies. So I have sort of DC on this side and DC on this side, but very high frequency AC in the middle of the circuit, okay? Now, the beauty of this is, as compared to say, this perhaps most closely resembles a flyback converter for those who are familiar with that topology, except that this topology is entirely soft switched, and I can turn up the frequency of this orders of magnitude to the point where I can get to the point where this transformer, instead of implementing it as some wound component, I might be able to just implement it as a printed component right in a circuit board. So I might be able to realize it as a set of layers in a circuit board with just printed transformer structures. The difference between this, however, and a conventional transformer is the fact that the inductance matrix of this structure is fully specified, by which I mean I'm using the resonance of this resonance with this network and this inductors, this parasitic inductors resonant with this network to get the performance I want that allows me to push up the frequency. Consequently, I have to have all the parasitics of this transformer very precisely controlled in order to turn up the frequency, okay? And consequently, that's a very different kind of design than one traditionally gets. So what do we have to do? Well, if I told you, okay, here's some transformer structure, tell me what the inductance matrix for the structure is. That's a solvable problem, at least computationally, okay? If I wanted to do the inverse problem, tell me, give me a transformer structure that provides precisely the inductances I want to get this high performance, that's a much harder problem. And the way we do that is by computational searching techniques to trade off size and efficiency to get a miniaturized system. Okay, so what we're doing is then burying the passive component as a planar batch fabricated structure, but I have to very precisely control that in order to achieve it. I should also point out that there are trade-offs in this design related to the power switches. When we built a lot of our early very high frequency converters, we tended to use very high performance transistors. So, it's not very practical, however, to use a $75 transistor in a 10-watt power converter, right? This is sort of a practical mismatch. So in this kind of space, what you really have to do is have all your power devices and all your controls integrated in a low-cost semiconductor process. So the question is, can one use sort of power semiconductor processes that are designed for 100 kilohertz to maybe a megahertz switching frequency at tens or hundreds of megahertz? And the answer is you can. In order to do that, you have to do a few things. One of the things we showed that you could do is, first of all, through circuit and device co-optimization. Instead of optimizing for the traditional metrics, what we showed you could do is, if you know the kind of resonant circuit design you want, you can find what the trade-offs are between the transistor parameters, how you shape the transistor layout, and the circuit design, and optimize that. And secondly, it turns out you can take advantage of the soft switch nature of these topologies, that you only turn them on under 0 voltage, to change what the required transistor lengths are, because you don't have hot carrier limitations. If you combine those two, what you can find is even in these low-cost integrated processes, you can run them at tens of megahertz, even though they were originally developed for hundreds of kilohertz. So I'll show you an example of this, and this is just sort of a layout of the chip that we designed to do this. And the most important things I'd like to point out to you are, first of all, we have an optimized power device on board using the optimization techniques I mentioned. Secondly, we have a resonant gate driver on board. And what this thing does is basically you turn on this transistor, you charge up this inductor, you resonate charge onto the gate of the power device, the charge resonates back off the device, and you recover that gating energy, or substantial portion of that gating energy. And because we have all the integrated devices and controls, we can set up all the sort of the detailed control logic to sort of manage that even under startup and all these other conditions that would otherwise be very difficult to do. Here's the prototype system we developed. In this particular case, it's a 6-watt, 75 megahertz isolated converter. Here you can see the IC with the optimized transistors. Here you can see the printed circuit transformer. This is essentially the isolation barrier here. It's more or less 8 to 12 volts input, 12 volt output, very typical kind of gate drive power supply thing implemented in a bipolar CMOS-DMOS topology technology. Here you can see the resonant gating. This is at 75 megahertz, so this is the half-sign resonant gate drive. So we dissipate about 1/3 of the gating energy that you would if you tried to hard gate this. Here you can see the sort of soft switch resonant format. So the transistor voltage here is approximately a square wave, like it would be in a conventional topology, but it rings down naturally to 0 voltage so we can turn it on, and that's what enables us to get to this very high frequency. I should note, by the way, that that's sort of the equivalent of a flyback converter. You can do other kinds of equivalents to more conventional topologies. So here's a version of a boost converter, same IC but different layout. And again, you can see we have the passive components printed directly as part of the circuit board. So that's essentially batch fabricating a good portion of your passive components. And you can see here, just as with lower frequency designs, you can get to higher efficiencies and higher power densities with a sort of a direct converter than you can with an isolated and indirect converter. That's coming back to my point that the requirements you place on the converter have a lot to do with how efficient and small you can make it. But where does this end up, right? So that prototype was at 75 megahertz. That's roughly more than 100 factor of 100 higher in frequency than a conventional equivalent design. What I've plotted here is the power density in watts per inch cubed versus the converter efficiency. And I've included a number of commercial converters, recent commercial converters. Here we are up here, and the answer is you get about similar efficiencies, but you get a power density that's a factor of 3 or better higher. Now, I went up more than a factor of 100 in frequency, and I only got about a factor of 3 in power density, and that's because I had to make up for the fact that I've now gone to a batch fabricated printed magnetic structure with no magnetic materials, so that forced me to drive very far up in frequency. And nevertheless, I can get a factor of 3 in size and better integration and consequently better reliability than I can with a more conventional design. I have a second example I'd like to show you. And this example is now more at grid voltage. So this is the kind of thing you'd plug into the wall in moderate power levels. And this is for an LED driver. So you saw the earlier LED drive, picture of the earlier LED driver. So I'll show you what happens when you try to push up to much greater frequencies. And in this case, instead of using, and the reason I wanted to show this, instead of having integrated devices, we can now use discrete devices. And instead of being at VHF, which is, say, 75 megahertz, we'll be in the range of 5 to 10 megahertz. So to give you sort of a notion of this, in this case, we not only have to address loss, say the switching loss, we also have to address circuit parasitic limitations on turning up frequency, which I'll describe in more detail. But before I do that, perhaps I should give you some background of what does this kind of application typically look like today. And these are a couple of commercial designs that you'll find. Typically, the efficiency of these drivers, and we've taken apart many of these drivers just to see what the envelope of performance that you get is. Typically, the efficiency is between 60 and 90%, and 90% is actually being generous. I don't think we actually found a commercial design that was that efficient. Switching frequencies are on the order of 100 kilohertz. This one's 57, this one's about 100. Consequently, you get power densities that are below 5 watts per inch cubed. Okay? Now, another measure of what's important in these drivers, or what you would like in these drivers, is power factor. And power factor is really a measure of utilization of the source. In some sense, you can think of power factor as meaning how much dissipation do I induce back in the utility in order to draw the power I'm drawing from the utility. So it's not a measure of my own efficiency, it's how much am I hurting the utility. A power factor of 1 is basically doing as best as you can. A power factor of 0 is, basically I'm sloshing a lot of energy and dissipating energy in the grid, but getting none. The goals for these kind of converters set down by the government for a power factor of 0.7 or better for residential designs and 0.9 or better for commercial designs. To tell you the truth, of all the ones we measured, there was only one design that actually had a power factor of 0.9, and some of them were truly atrocious. So that's one thing that a lot of the commercial designs throw out the window, even though there's guidelines that you'd like to meet. And it turns out there's no laws about power factor below a certain power level, and these are below that power level. So overall, you're looking at relatively low power densities, kind of crummy efficiencies, and bad power factor is what you've got out in the market today. Now, I'd like to point out one other limitation, and this has nothing to do with whether you're at high or low frequency. This just has to do with converting between AC grid and DC. If I'm going to convert between AC and DC, suppose I want to put constant DC power out, okay? I can't possibly draw constant DC power in from the line, right? When the line voltage crosses 0, it doesn't matter how much current I draw, I'm going to draw no power, right? So what happens is if I'm drawing good power factor from the line, high waveform quality, my power inherently pulsates, okay? Because my power instantaneously that I'm going to draw is going to vary with the instantaneous line voltage. And as a consequence, my DC power output's constant, my AC power input's pulsating. I have to buffer some amount of energy in the middle of the converter that's proportional to the output power, average output power, and inversely proportional to the line frequency. So this has nothing to do with the switching frequency of the converter. This has to do with the AC line frequency. And consequently, I'm going to have to store energy in the middle of this converter, and that's going to set some limit on the size of the converter. And here you can see this is a laptop adapter. And here you can see about 1/5 of the laptop adapter is devoted to buffering that line frequency energy. That's right there. And typically one uses electrolytic capacitors. Their peak energy density is sort of the highest that you can get. The problem with that is they have both temperature and lifetime limits. So in some sense, it's undesirable, but people do it because that helps them make everything smaller. And as you can see, it's already a pretty large portion of our system. So what we would like to do is find a way to make this energy buffering as small as possible. And as a secondary goal, we'd really like to get rid of the electrolytics because there are a substantial temperature and lifetime limit on the power electronics. And if, for those of you who have had things like the curly fluorescent lamps that burn out all the time, the electrolytic capacitors dying in those is one of the classic failure mechanisms of these things. So they really do hurt your performance of your system. So let me describe what one of the constraints are in turning up the frequency in these kind of LED drivers is, right? So I'm going to convert from grid voltage, AC voltage, but peak voltage up to, say, 200 volts, down to low voltage DC, but at the input side, I'm coming in from high voltage and relatively low current, right? So high voltage and low current is high impedance, all right? High characteristic impedance means essentially I have relatively large inductors and relatively small capacitors. If I turn up the frequency, suppose I want to just dial frequency in my circuit, what that turns into, instead of large inductors and small capacitors, I get medium-sized inductors and ridiculously small capacitors. And the problem is I very quickly, as I turn up frequency, scale out of the range where I can realize that because my intrinsic device capacitances that I need to carry the current are too large for the system, okay? So that's a different constraint besides just loss, it's just component value scaling that prevents me from going up at high end frequency as I'd like in order to miniaturize my system. So in order to deal with that, we have to come up with circuit architectures, and we do this two ways. First of all, we pick circuit topologies that are adapted for very small magnetic size, relative to other topologies. And that, because I have smaller magnetic size, I have larger capacitor size, I can scale up further in frequency. And secondly, what I'd like to do is voltage stacking of my subsystems so that each subsystem has to deal with lower voltage, it operates at lower characteristic impedance, and again, it has smaller inductors and bigger capacitors that can go up higher in frequency. So these are sort of two tricks we're going to play at the architectural level to let us scale frequency. Okay? So here's a circuit topology that I'm going to illustrate for those who are circuit designers. And this is what would be known as a resonant transition inverted buck converter. Kind of a mouthful, but essentially here's the idea. What I'm going to do is I'm going to turn on this transistor. I'm going to ramp up current in this inductor. When I turn off the transistor, I turn it off at 0 voltage because of this capacitor. I deliver my energy to my load. So in the first part, I have the transistor on, the current ramps up. Second part of the circuit, the current ramps down to 0. When this reaches 0, this inductor rings with the net capacitance of my diode and transistor, and the voltage rings down for 0 voltage turn on, right? So that's that low switching that I need to go up to high frequency. But here's the key point of this topology, is not only does it give me this 0 voltage switching, but because this has very high ripple in this inductor current, that's a relatively small inductor, which means I can use relatively large capacitance here, or equivalently turn this circuit up higher in frequency before I hit the wall, okay? This is just to illustrate, this is just this circuit subblock I'm showing you. Now I mentioned that a typical switching frequency in this kind of range is on the order of 50 to 100 kilohertz. This particular operating point is 7.8 megahertz. You can see the high ripple in the inductor current, so it's a small inductor. You can see the ring down for near 0 voltage switching here so that I can have low switching loss at this frequency. And even though I'm operating at this relatively high frequency in this regime, you can see I'm between 95 and 96% efficient, okay? So we can get very high efficiencies while operating at very high frequencies. So the other thing I said we're going to do is we're going to use a stacked architecture so that I can reduce the voltage processed by each circuit block, and that'll help me keep the frequencies high. And I'm also going to use that to get rid of those electrolytic capacitors. And how I'm going to do that? Well, first of all, those individual high-frequency converters, here's one and here's another one. So I'm going to have two outputs to this first subsystem. And each of these are stacked in series. Now there's two capacitors here. This capacitor, this capacitor is a very large, relatively large capacitor. So that's where I'm going to buffer that line frequency energy I mentioned, right? So I'm going to swing that energy, the voltage on that capacitor up and down to store the energy in the middle of my converter. The second capacitor is a very small capacitor, and that's taking up the difference between whatever voltage needs to be on this capacitor and the instantaneous line voltage at the input of my circuit, okay? The other function of these is to divide down the voltage so that I have sort of half the voltage, roughly speaking, on each converter, okay? Now, what I'm going to do is I'm going to draw current from each of my two converters, okay, such that I can have a high-quality, high-power input power factor waveform and buffer the energy here while providing totally constant output power from the two outputs of this converter stack, okay? This just shows what the sort of approximately the input current of such a circuit would look like, okay? It's not a perfect sine wave, but it's relatively high power factor. And as we modify operating range, we can control the input wave shape that we draw, the current wave shape, to meet these constraints, high power factor and constant power delivered to the load. So this is what the overall circuit looks like, okay? These two resonant transition inverted buck converters, each of which only run at roughly half the full system voltage, and they can run at very high frequency. And then I'm going to take the output power of one of these. I'm going to use a switched capacitor circuit to transfer it to the net output, the single output of the whole converter, okay? And the benefit of using a switched capacitor technique is with a switched capacitor circuit, you can get very high power densities and very high efficiencies, but they can't regulate. That's the sort of a circuit design trade-off in these devices. So what we're going to do is we're going to use the first stage to do the power factor control and the regulation, and the second stage to just shuffle energy among the two outputs to combine it to a single output, okay? So what do you get if you do this? Well, here's a prototype system we built, and I'll first of all point out a couple of things about it. First of all, we've gotten rid of the electrolytic capacitors. In fact, we're doing all of our energy buffering on ceramic capacitors right here, okay? Secondly, you notice that this circuit does not have very much in the way of magnetics. Here's these little red things here. That's the magnetics. If you remember the earlier picture of an LED driver I showed you, the footprint's approximately the same. But instead of having this huge inch-high stack of magnetic components, I got these two tiny little magnetic components. That comes from A, having topologies that minimize the magnetics, and B, the fact that I'm running, instead of basically 2 orders of magnitude higher in frequency than a conventional design. Okay. Third, I'll point out that here we can see the energy buffering. This is the voltage on the energy buffering capacitor. Because I'm swinging it over a wide range, relatively speaking, to the peak voltage, means that I can take advantage of multi-layer ceramics, which have a lower peak energy density but a higher usable energy density if I swing voltage across them. And I should say, by the way, the efficiency of this overall converter is on the order of 93%. I said none of the commercial stuff was more or less exceeding mid-80s. So I actually have, despite the fact that this is much higher frequency and much smaller, I have higher overall efficiency, substantially higher overall efficiency. And lastly, the power factor's 0.89, which is approximately that, I said 0.7 or 0.9, depending upon the market, was the right number. This could be above 0.9. Our initial prototype was just a little bit off. But how are we doing on our miniaturization goal? Well, this prototype I'm showing you was 25 watts per inch cubed, or about a factor of 5 higher in power density than typical commercial designs. In fact, I don't have the picture of it. We actually redistributed the capacitors on the second and rebuilt it so that the box power density was approximately 50 watts per inch cubed, or 10x the power density of typical designs today, okay? And in fact, if I looked at the displacement volume, it's actually, if I could lay out these components better, it's actually 130 watts per inch cubed power density, or a factor of 25 better than conventional commercial components. All right? If I look at the actual breakdown of where my volume is in the system, the number one thing is actually just the circuit board. Well, that's clearly not true of conventional power electronic components. The number two thing here is the actual energy buffer, which I said doesn't really relate to the switching frequency. We've managed to make it somewhat smaller and get rid of the electrolytics by the way we're swinging energy from the circuit architecture. That's actually independent of us going to very high frequencies, but it shows you that if you use the right kind of circuit architecture, you can minimize those constraints. So essentially what we've got here is a design that's roughly 10x smaller. It's more efficient and has higher power factor than anything commercial you're going to find. Okay? Now, I wanted to point out that in terms of going to very high frequencies and making much, much smaller power converters, we're looking at designs here in these two examples that are between 3 and 10x better in volume than conventional designs. I would argue that we actually don't even know what we're doing yet. In other words, by sort of jumping far up in frequency, there's clearly the opportunity to do much better on size and performance than people have achieved to date, but we're only scratching the surface of the ways you can do this. There's a tremendous amount of room for improvement. And in fact, a lot of the techniques that people have developed at much lower frequencies for getting higher performance, for example, other kinds of control methods such as phase shift control. This is a phase shift control one going at 27 megahertz. You can use synchronous rectification, which they use at lower frequency converters. This is a synchronous rectifier design in CMOS at 50 megahertz. All these kind of techniques that people have pioneered at low frequencies can be ported, but with changes up to very high frequencies. So there's tremendous, and we're not even using any of these techniques yet, right? So there's a tremendous room for getting much further than we've gotten thus far. I should say that there's also room for a lot of improvement on the devices and materials front. So, for example, what we've done thus far is used either coreless designs, which I showed you, or just commercial RF magnetic materials, and I was only doing that at 5 to 10 megahertz. It turns out you can take advantage of bulk RF materials, if you find the right ones, out to about 50 or 60 megahertz in switching frequency. Above that, you really start to move to coreless designs, except that there's new thin film anisotropic materials that are being developed that can actually even go out to beyond 100 megahertz. So this is material actually currently being developed by Professor Charlie Sullivan at Dartmouth, who's coincidentally a Princeton alum. So I would argue that once we start to first not only further exploit these devices, but materials, but to develop materials which are really targeted at this, which don't really exist today, because that's not where the power electronics industry is in volume yet, we'll even do far better than we've been able to do in these prototype designs. So to conclude my talk, if we can manage to make major jumps in switching frequency, say 10x to 100x times conventional designs, we have really the potential for getting miniaturization, which I showed you, integration, which I showed you in one example by integrating the passive components, and bandwidth. And I didn't really illustrate the bandwidth performance in either of the examples I showed you, but it naturally comes along. If I'm going at much faster rates, I can get much higher bandwidth. To do this, we've got to overcome device and magnetics losses and also manage the parasitics in the circuits and overcome some of the inherent constraints about sort of component sizing. Nevertheless, with the appropriate design methods, we can get to these greatly increased frequencies. And I should note that the correct strategy for doing this depends upon the operating regime, the voltage and power and the device characteristics you're using. And that's why I tried to show you one that was sort of an integrated device strategy and one that was with discrete devices. And I've shown you two operating regimes, sort of moderate voltages and low powers and high voltages and moderate powers. We're also currently doing designs at much higher voltages and higher powers, so that there are variations in how you would do the designs to really jump this frequency gap that vary on the application space, but it's applicable across a very broad range of cases. And lastly, I'd say that we're only scratching the surface. We're nowhere close to what's achievable in these in these kind of power electronics designs. And if we can achieve that, we can start pushing these designs into all kinds of applications, whether it's LED lighting, photovoltaics, power supplies for computers and communications, and a host of other applications. And with that, I'll be happy to conclude my talk and take any questions you may have.
Over there?
I've always kind of wondered about, your wall warts got really small with the transformer basically out of the wall wart, and now they sort of have. Oh, there's a microphone. So I've always kind of curious about power factor. So our smaller wall warts that we have today are presumably doing horrible things to our power factor, and I think the stuff you guys were sort of showing is a little bit better, but sort of the same idea that's not drawing all the way around, because the first thing you go through is not a transformer, it's something else which is only drawing on certain portions. At what point does the power company actually push back on us? Because I really wonder if everyone were to start drawing all of their power with sort of very, very poor power factor devices, are they just going to basically sort of throw their hands up and say, stop doing that, or something worse?
Yeah, they already do. If you're at industrial power scales and you draw a poor power factor, you get charged for that. And in Europe, particularly, standards are emerging for higher, the higher power devices. And even in the United States, there are, to get some 80+ certifications or Energy Star certifications on your devices, people are starting to look at either THD or power factor as a constraint. It is estimated, I've seen some estimates that claim, and I don't know if these are true, that these are government studies that suggest that up to 2% of the dissipation owing to commercial buildings is because of poor power factor and all the power supplies in those buildings. So if that's really true, then a couple percent of the energy dissipation that all the generators in the country have to permit just because we have crummy power supplies is a tremendous penalty. You're correct that the one I showed you didn't actually get very good waveform, or you could say that's not very good waveform, but keep in mind, that's 0.9 power factor. That's what people want to get to. If I showed you what the power supply for my MacBook here was doing, you'd shrink in horror. It actually looks like an impulse at the top of the line and an impulse at the bottom of the line, and that's what it looks like. And I don't remember what the power factor is, I've measured it, but it's well below 0.5, and it really is causing those problems.
Related question. What's the sign of the power factor typically? Is it inductive-like or capacitive-like?
In the ones we've built, it's almost resistive. It's mostly distortion factor that's, you're asking of the commercial power supplies or?
No, well, yeah. Let's say you said typically, it's somewhere between 0.5 or 0.7 or something like that.
Yeah, mostly those are distortion factor. That is